Nice to see you all here. So today I will be talking about Lustre Metadata Writeback cache. And so let's see, why would that be important? Well, cache in general is key for good performance, and we have all sorts of caches. I guess the underlying reason is having everything super fast is not really, feasible money-wise. So people try to save money and have slower tiers, but then they want their performance like it's a, like if they paid the top dollar, so they just pay a little bit of money for the fast storage and then try to have the hot data over there, and that's how it goes, right? So the data is well cached in Lustre. We have page cache, and everything goes through that. Thanks for Lustre Linux kernel implementations. But the metadata isn't as well supported for that. Like the reads are okay, but everything that does modifications has to be sent to MDS. That's a synchronous RPC, and that gets bogged down in network latency and things like that. But metadata performance is important still, and so because applications do tend to create lots of files, they do tend to do other operations. There are millions of RPCs sent over the network, so I kind of set out to see how that could be improved for at least more important use cases.
Do we still have persistent memory in the pyramid?
Excuse me?
Go back one.
Sure.
Do we still have persistent memory? Should we still have persistent memory in the pyramid?
Sure. Why not?
Who's producing
Everybody who attaches a battery to DRAM stick, right? Also, there's old stock of, I want to say unobtainium, but that was like the Intel thingy, right?
Crosspoint?
Yeah, but there was a better name that better rhymed with the unobtainium, right?
That's discontinued.
Yeah, I know, but there's old stock, right?
Okay, sentimental reasons.
Yeah. So let's see about the Lustre, current data cache acceleration inside Lustre. So we do have persistent client cache that Andreas talked about, which is basically local storage on clients for read-only or exclusive file access. It does require some pre-staging to ensure that the data you want to work on is actually there when you need it to be there. Then there's the Lustre on demand, which is basically a small Lustre file system spun up on nodes local to your clients for faster access to your hot data. Again, that kind of needs staging and out, but some people find that producing them decent results, not obtainable otherwise. We also have data on MDT for accelerating data that comes in small pieces. So you go to MDT and get all your data together with metadata, reducing RPC latencies and stuff like that, which helps for like smaller chunks, I guess. We have OST pools for SSDs for cache. So, again, your hotter data goes there, and when you when you try to fetch it, it's faster than going to the, spinning Rust. And of course, in memory, everything's fully cached data-wise. We have the buffer cache that Patrick seems to dislike so much. He's, on this, like, let's not cache it. But I mean, in reality, lots of applications still have lots of reuse. So this kind of cache is still very important. I'm sure LNL could tell us all about this because they actually tried to run with direct I/O only back in the day and very quickly realized that only well-behaved applications of a certain kind could operate like that. And so this data is protected by LDLM logs. So it's all fully consistent. You could see it on all the nodes. One node's write, the other node wants to get it. The LDLM comes in and facilitates the transfer. And so it's all very seamless, working very nice. But the metadata doesn't have a bunch of that. And like one of the last pieces that is needed. And so if you look at how metadata caching is implemented in the field, there are basically several approaches. The two most common one is for what shared block file systems do. And for them, it's kind of easy, right? Metadata is just data. It's just a block, and the client, when it wants to access that block, it just obtains a lock, gets a block, interprets it, and suddenly it works just the same as a local file system. So they could do their modifications, everything they need to, and if works like real well if there is no contention. But if contention does come, suddenly it all crumbles very fast. So another client comes, you need to flush the whole block or more to the server before the other client could get the same block, do their modification, and if there's another conflict, this kind of block ping pong continues, and those blocks could be quite big, so the result isn't very fast. So to address this contention, people try to play various tricks. So there's no shortage of libraries that try to exchange like metadata for data performance. So I mean, many kind of libraries like that. I became aware of them at JLUG one year, where Riken was presenting about their slowdowns on Fujitsu file system. And they had an interesting graph that said that, oh yeah, we have like 80 creates per second, that's several thousands clients trying to create files in the same directory. And so we found this GPFS targeted library that helped tremendous deal. And so I went to check the library, and the library had a very interesting graph that basically showed you that when a couple hundred clients were trying to create files in the same directory, the performance on GPFS dropped to, file creates per second, which was like, that's like really low, because in Lustre we could do easily like, tens of thousands and more just with a single MTS. So it looks like GPFS tried to address this by, having a bit of a hybrid approach. They try to send updates with metadata blocks between the clients and other similar things. There's like people complicate matters by trying to reduce lockable block sizes. It looks like with file systems like GFS and I think OrangeFS, they basically limit number of actual clients that could be had, and instead they like if you need more, you are supposed to re-export that as NFS, and then kind of lots more clients come through NFS, and then that's aggregated to a small number of actual, block file system clients, and that also kind of reduces the contention. But, disadvantages with this approach as well, of course. And then there are file systems like Lustre that is not a shared block file system, so metadata is actually interpreted on the server. So the clients just see pieces of metadata. When you want to look up a name or open a file in a directory, you tell the server that, hey, there is this directory and I want this particular name in it. And the server replies to you that, hey, sure, here's your information. When there's conflicting access, this works great because, say, I have 1,000 clients all trying to create a file in the same directory. That works nice. They all send their, like, hey, create me this file. The server gets all those RPCs. All the locking on the server is local. There's no blocks bouncing all around. It creates things as it wants to and distributes the replies, and the result is like tens of thousands of creates per second easily. And if you, have DNE and things like that, that goes up even more. But the problem is when there is no contention, that's actually doesn't become any faster, and actually even slower because of how many RPCs you have in flight. If you have a single process trying to do those creates, then, it's just RPC to RPC to RPC. You couldn't just send all your creates all at once from a single threaded application. So to address those uncontended cases, also various tricks are being played. So CCI that Andreas talked about yesterday, is basically you have a regular file system image like ext4 that is stored in a file, and it's mounted locally on those clients that needs access to it. And it works like a shared block file system, except you couldn't make any changes because it potentially is seen by more than one client. Or you could make changes, but then it must be seen by exactly one client because all the caching otherwise would totally ruin the file system. And of course, then there's all the, all the mounting and other such hassles when you actually start the jobs that depend on that. And so I was kind of exploring it, and it dawned on me that, in a way, maybe like the Linux de-entry cache, the VFS, is a file system in its own that could be used, for this kind of things. And the testament to that is the so-called RAM file system that's available for, initial RAMFS and such. And so the approach I chose is, like, every time you try to create a directory, we should get an exclusive lock on this directory, and everything that happens under that could be client local. You don't need to talk to the server because, say you want to create a file under that directory. You already know there are no files inside. So you could create any name without checking. Or if you are creating a second name, you already know that the existing name is there. So again, no need to check. And so it's all fully local and fully populated by new creates. And eventually it could be extended to fetch the whole one level deep of names, so that it could work on existing trees. And then all operations become node local, shared block file system, but there is no block underneath. It's kind of real fast. The granularity of such lock would be a whole subtree underneath, and the whole idea sounded almost too simple to work, but actually ended up working. So here's the rough idea of how it looks like. So client on the left has their part of the tree, client on the right has their part of the tree that server actually doesn't know fully exists. This line is basically the name of the tree, but everything underneath is fully client cache contained. And the other benefit that we would be able to get then is batching of those modifying operations. So when an application tries to create something, there is nothing to batch. Like, you couldn't just stop and wait, like, hey, let's see if they want to create something more. That doesn't work, especially if it's a single-threaded application that is waiting for the result of the first creation before they move on to the second. But here, we have this whole bunch of stuff that we could actually send as a whole to the server. And in fact, we could even merge updates, like, create a file, do some changes to it, rename it, and then remove it. Why even let the server know about it happened, right? If it's a tree fell in the forest and nobody saw it, did it really happen? Except maybe for the audit folks. And I mean, I don't know how much do they care about that case. So, I mean, they have a special mindset that is sometimes hard to look into. So if you have strong opinions about that, let me know. Or, I mean, of course, it remains to be possible to just disable all the optimizations and let the system really, really crawl. Well, I mean, end users don't like that, but then you have the full control, right? So, and on the topic of batching, we actually have we already have metadata read ahead in Lustre that's called stat ahead. This is when we see that your application is trying to, iterate a directory or something, and we predict that you will iterate more entries. So in this specific case, we could try and apply the batching logic, right, without any other changes for any other caching. And so we decided to actually implement this as a, as a separate implementation, because as Andreas likes to put it, it's bad to have this huge feature that takes years to develop because priorities change and all sorts of other problems happen. And so when you have small chunks that keep coming, if you stop, eventually, at least all the stuff that came in. And so we are targeting this for 2.16 release, which is hopefully soon. Most of it has already landed. Basically, like existing, like send a whole bunch of stat RPCs is getting replaced with send a single RPC asking for all those other files. It adds detection of how your iteration is going. Like, are you diving into the directories first, or are you processing the directory first and then dive into the directories, which is breadth first and depth first. And we support, strided patterns for alphanumeric order traversal, and MD IO 500 test. Easy and hard basically show pretty decent improvement, so I guess it works. But returning back to the actual metadata writeback cache. So how would you handle the contention of this bubble that hangs off of the tree? So like say another client comes and tries to access a file in this tree. I mean, it doesn't know the file is there, right? But there's like going to be a pass that it tries to look up. Or maybe somebody just does CD and tries to ls. They'll just bump into this exclusive lock, and the client that does hold the bubble will get a notification from the server that, hey, look, somebody is trying to peek inside, so you have to tell us what's inside. But just flushing the whole thing would be both expensive and probably not very smart. So what we do instead is we just flush one level of entries, and the bubble kind of splits into a few and drops one level. So instead of one kind of lock, every directory created underneath gets its own lock. And so like if you do ls, you see that, hey, look, there are all those names now. And then the client that is trying to do this conflict access could continue descending whatever path they are interested in, while the rest remains fully cached on client 1. So I have an example on how that actually works, I guess, that hopefully is clearer to understand. So we'll start with somebody trying to untar a Linux kernel. The Linux name is known because it's fully, it's referenced from the Git directory that is entirely on the MDT and is already committed. And then everything under Linux is in the cache, and nobody but the client with the cache knows they even exist. And then there's another client that tries to ls a file that they don't actually know exists, but they suspect it does. And so at first, they try to access the Linux directory. They send a request to MDS that, hey, tell me about this Linux directory. And the MDS sees that this directory is actually having the lock. So they tell the client that holds it that they need to provide the information. And then the client ends up just flushing the entries under it. So all those subdirectories are created, the locks are obtained and remain in the cache, which happens kind of much faster than if we tried to flush the whole thing. And the client too gets its answer, and then it moves on to the next path component, and it asks for the drivers. Again, the MDS gets the message that, hey, we are interested in the drivers. It sees that there is a lock, so it contacts the client 1, asks for what's inside the drivers, and the client, again, it just flushes the content of the first level of the drivers dir. There are some more directories. That same thing repeats for the net dir. Again, the directories are flushed, and also a file. There's a file for which the name is finally created, which is kind of important, and I'll cover it later. But basically, you can see that only things that get conflicting access end up being flushed, and everything else remains in the client cache for as long as practical. And so, basically main targets are, we'd like to utilize cache servers, client side instead of the server side, because it's much higher acceleration compared to, because of the metadata locality and all that stuff. Of course, the downside is, the code gets more complex, but, basically, most of the time, code gets more complex if you want to get better things. Mostly, anyway. It does give us ability to delay and group metadata flush instead of always doing the synchronous RPCs to MDDS, which is mostly beneficial. There are some cases when it's not, but mostly it's beneficial. Just need to create a mechanism to actually allow that. Also, cache on volatile memory instead of persistent storage is much faster. It's just you need to ensure you flush it every once in a while, otherwise it gets lost and people get upset. And we still want to keep strong POSIX semantics, because if you don't, we end up with situations like NFS where people do things as they expect on their local file systems, and then something happens and they're confused, like, hey, this looks on my laptop, but doesn't work. On the system, that never works well. We've learned that lesson long ago. Just means the more complex LDLM log protections that are needed to actually make it work. And so we have to figure out, or I guess we've mostly figured out flushing and memory control, and basically the metadata flash would happen either when there's a conflicting access from a different client, or when there's a memory pressure on the local host, and we couldn't contain all the cache inside anymore, or there's the data have been sitting in the cache for too long, and it's probably time to flush it, so that should something happen, it's actually persistent. And we could do the quick flushing using bulk RPCs and stuff. This is the rough outline of all the components, and basically, it really is a VFS cache that through the callbacks allow us to plug into this great wonder of Linux engineering, and through the policies allow to decide how well does it actually work. Like, do you want to create the writeback bubbles in this directory? Don't want to have it in those other directories? Do you want to try to flush to attached persistent client cache instead of going to the server? Things like that. LDLM does its usual job talking to the servers. And now back to the files. So in that one of those diagrams, when it's called metadata writeback cache, but by necessity it actually caches both metadata and data. And this is because if a file is only known to the client, you couldn't store the data on the data servers, because there is no layout to attach it to. So the memory for the data pages is also there in kind of anonymous manner, all the way until the file is actually created on MDT. And at that time, the layout is created and the data pages are assimilated into the proper Lustre structures for the OSC or metadata or data on metadata MDC structures. Yeah, so which does mean that all the prior levels of metadata is actually known to the servers first. Like, you couldn't create a file in the middle of nowhere not connected to anything. Yeah, and so yeah, it's, all the flashes in batches allow great acceleration. Maybe eventually we'll integrate with persistent client cache, and if I really take that big whiff out of this pipe, eventually we might even have disconnected aberrations and then eventually reconnect just to sync up. You know, a big whiff. Yeah, some benchmarks results. So this is a synthetic single node MD test, and you could see that there's a pretty big boost everywhere for, you know, using the metadata performance, metadata writeback cache. On certain operations, we almost approach the TempFS performance. Some others we don't, but it's probably just a matter of looking into it and seeing where's the extra additional overhead we haven't accounted for. Because really there should not be anything standing between us and achieving near, you know, RAM performance on this. So this is the multiple metadata performance on the same synthetic benchmark. Again, you could see it scales kind of well. We've tried some real-world workloads, so a file bench default workloads show again that performance boost is very noticeable. And we also tried common things like, you know, untar a Linux kernel source tree and try to do things on it. And that was the workload I was mostly aiming at when I first started to think about it. Because you always hear from users that, you know, I have this application, I untar it, and then I try to build it, and it's so slow, but I have to do it so that it's then visible to all my compute nodes when I run my job. So this particular workload does really, really well, as you could see on the right. There's, you know, in many cases it even beats ext4 because it's just, you know, all dcache. We also tried a pathological workload where you try to parallel untar things, and there's actually constant conflicting. And even there, because of the batch RPC aggregation, we still come out ahead. So there's no, like, I was fearing that maybe when conflicts are too much, all the extra overhead would slow things down, and that actually does not happen, which is a nice thing. Yeah, and, you know, some more benchmarks, like trying to untar a file to Lustre, NFS, ext4, TempFS, and Lustre with writeback cache is also showing you nice boosts. And I guess NFS is dragged down by them only having the single servers that everything goes through. So, you know, they end up being the slowest. Yeah, some synthetic benchmarks show that we could easily get like 100% improvement in certain operations again. You know, nothing to sneeze at. And some more synthetic benchmarks. Yeah, so as you know, metadata writeback cache will really accelerate everything. So batched RPC support is coming in 2.16, and we hope for the complete feature going into 2.17. Yeah, and any questions?
This will be very nice to have. Yeah. Questions? Olaf first.
Pretty cool. I have two questions. One is the batched RPC support seems like it could, could produce performance benefits even without the metadata writeback cache. Is that something that might happen in the future so that you could, I don't know, say if you have a node that's getting lots of creates or lots of makers happening by multiple processes at the same time, that they get batched? And
so it does come before the entire writeback cache, but for a different scenario where a node is trying to read things, because you couldn't really pause creations on a node waiting for more things to come. It's actually going to introduce extra latency for you, and it probably makes no sense. Like, first of all, it's even hard to know if there's a parallel creations are going that could be aggregated. And even if it could be done, that means that you still introduce extra latency to whoever came first to do their RPC.
Okay. And then the other question is, in the case of a file system that's having problems, we occasionally will have a case where one router of many routers goes down, and now some percentage of messages get through, and Lustre gets all cranky, and we get disconnects and reconnects and that sort of thing, or perhaps server hardware is having trouble. In a context like that, if I as a human had a choice, I might want to tell the system somehow, okay, get all the data onto the servers and stop producing file system information that's on these clients that may never make it back if the problem gets worse. Is that something that might make sense to make the system detect bad situations like that?
I'm not entirely sure what the problem is, right? So if you have network issues, basically they are either recoverable and eventually the messages will get through, or they're not recoverable and the client might eventually get evicted and lose all its cache. Especially with cases like write-back cache, this is very undesirable. And so we've been having some discussions about how uncontended pieces of the tree should probably survive eviction as long as nobody else tries to write in that area anyway. And it sounds like that might be the answer you're looking for here. Like temporary problems, the client is kind of, it could still do the local operations. It could be evicted from the server, but retains its cache to be flushed later when the reconnection actually occurs, and is robust enough to carry out all those RPCs.
Thank you.
I know James has a question. Any other questions?
So for the memory you're using for the WBC, is it CPT aware so we can partition it away from our applications as far as possible?
It's possible. I mean, the standard policy for the entire cache in Linux is try to be local to the application, because it's the application that wrote it that is going to read it. But nothing stops you from doing a different policy and migrate it away. It's just going to become somewhat slower, but if that's acceptable to you, I don't see why not.
It's just that the big issue is the noise issue.
Right.
This is awesome, first of all. I had a question about lock storms. So if you were to create 1 million directories under your root and then basically have contention against the root, are you then trying to get 1 million X locks on the directories you just created under there? I was trying to understand you had a slide in the middle that was said basically if you get kicked out, you're going to try to grab locks for all the children directories.
You mean when we flush the first level?
Yeah, if somebody tries to get access to the directory, you've basically taken a WPC lock on.
Yeah, so yes, we will have to get 1 million locks. I mean, this is the case anyway if somebody was trying to iterate that. Like, imagine you are trying to untar something with 1 million directories inside. Right now, you get that 1 million locks up front. So with write-back cache, it's delayed and level by level, which actually reduces the lock workload.
Okay. Yeah, your tar example was pretty close. I was just I was trying to think up a really nasty scenario like that. So it sounds like it works. The other question I had was, I'm immediately going to want to do this for imports because that's a huge thing in cloud, Lustre. So is the batching mechanism or the batching framework you've kind of set up, is that generalized or is that really specific to write-back cache?
It's not specific to write-back cache, so you should be able to use it for more things. You could see it's already in the tree, so let us know if it's missing some functionality, and we might be able to add it. Send patches, which is preferred way. Also, I guess I didn't show it, but the actual write-back cache is this LU 10938. So you could see the patches, you could play with them if you want to. It works. It's just doesn't always work, and this is why it's slated for hopefully 2.17.
Awesome. Thank you.
Any other questions?
Oleg, maybe this is too much, but you didn't mention much about how data is handled, because of course these locally created files, I mean, how is striping handled on them, and how does data get written out if it's written to these files?
There was an entire slide about that.
Oh, sorry, maybe I was, okay, I might have. It's not, oops,
No, not that one.
okay.
This.
Oh, yes, okay, I'm sorry. Sorry, I guess I missed that one. It's a problem with having seen these before, sorry, okay. All right, so you did answer that. Sorry, Oleg.
Oleg does not kid around. Any other questions? So 217 is the target for this?
Yes, that's what we hope for. You know, everything that's not the next release is hopeful.
Looks like 217 will be full of goodies. Okay, that means we need quite a lot of testing for 217.
I mean, that shouldn't mean you don't need a lot of testing for 216 either. The testing is ongoing thing. You don't want, you know, to skip something only to figure out in 217 that, hey, look, all that stuff in 216 was buggy as well.
Okay. So what's our criteria? This is a Peter question. I don't know where Peter is. Peter? Has he left? Maybe. What's our criteria for calling it a 3-branch instead of a 2-branch?
A what branch?
Lustre 3, Oleg.
Oh, Lustre 3. I don't know. Whenever Peter Brown gets another child, right? That's how it works with Linux anyway.
Okay, fair enough. Any other questions? All right. Thank you, Oleg.
Thank you.